Now this, what I'll be talking about in today's and maybe the next class, concerns quantum dynamics. You have already done that. Quantum dynamics essentially how does the wave function evolve with time. Now, wave function evolves with time is something that you already know because you have solved the Schrodinger equation for certain cases, so you know. What you know is essentially that the Schrodinger equation gives the way the wave function evolves is a PDE, partial differential equation, solving which we get how does the wave function evolve. And that is something we have also done. No, we have not done in the last assignment, but it was supposed to be the next assignment, which you have not yet done. But the basic idea was that you start with an initial wave function, and the way to compute without actually solving the differential equation was that we know the solution of the differential equation, that it can be decomposed in the components of individual eigenfunctions. So you take the projection of the initial wave function on the individual eigenfunction that gives the coefficients, and so the evolution, so psi x and t will be c1, then the psi1 of x and e to the power I e1 t by h cross plus c2 psi 2 x e to the power I e2 t by h cross, and so on and so forth. So all that you need to do in order to calculate the evolution of the wave function are to calculate these coefficients, which are nothing but the psi 1 of this. This psi is the initial psi. So this is your psi x comma 0, and this is the eigenfunction. So this is how you actually calculate, and you know the E1, E2, and E3 and all that. So by using the results that you had obtained in the first assignment, you can easily calculate this. And the part that I later deleted was that you just calculate this and plot it as a time varying wave function. You cannot plot the wave function itself, so plot mod psi square. Now, this is a way of doing that. There is another possible way of doing that, which I briefly talked about when I was talking about the mathematical part, where I said that the Schrodinger equation actually is I h cross t dt of psi. It will be function of time, x and time. So I write the whole thing. This is nothing but the Hamiltonian operator operating on psi. And you can easily solve. This is a first order differential equation, so you can easily solve. So that leads to the solution that psi x t is equal to e to the power minus I, the Hamiltonian operator here, time t by h cross times the initial time. So this is a exponential operator, exponential matrix, because this is a matrix. So it is the exponential of a matrix, and you know how to obtain the exponential of a matrix. This is another way of solving the problem that I gave in this assignment. All you need to do is to write down the Hamiltonian operator as a matrix, obtain this exponential of metric. So what you get, this term is called, this is also another operator. This operator operating on the initial condition gives the final condition. Okay, so it gives the final condition. This is called the time evolution operator. So the next assignment will be to actually plot the evolution of the wave function, the mod psi squared, by this method as well as by this method. Okay, so that you can get a test of both, and both should give the same result. And if you start with a narrow Gaussian, so suppose 0 is here, you start with a narrow Gaussian somewhere here, not at 0, at some distance, then you'll see how it evolves. It will actually oscillate and things like that. This is something I wanted you to see. So that will be the next assignment sometime. But what I'm trying to point out is that this whole picture is based on whole idea is based on a particular visual representation, that the wave function changes with time. And at any point of time, if I want to extract the information about anything, for example, what is the energy, what is the position, expected value of position, expected value of momentum, if I want to extract all this information, all we need to do is to operate by the appropriate operator and get the information. So the idea was that the wave function evolves with time, and the operators do not. And if the operators do not, their eigenfunctions would also not evolve. And since the eigenfunctions form the basis set, so the basis also do not evolve. Okay, so this is the picture that we had in our mind when we worked out all that, from the last semester to whatever we have done so far in this semester. Now, ultimately, what are we interested in? Ultimately, we are interested in the observable things, and the observables always come out as the projection of the state vector on the eigenvectors, right? So it is like if I draw a cartoon, I'll just delete this. If I draw a picture of the situation, it is a set of, sorry, I'm drawing badly. Let me use the straight line. So these are the basis vectors, and suppose this is my state vector somewhere here, maybe. So this is my state vector. This is my psi. And we are actually interested in the observables, the probability of different, what we actually observe are the eigenvalues of the operators, and the probabilities are given by these projections, right? Probability of observation, the probability amplitude is this projection, probability amplitude is that projection, and so on and so forth. Now, suppose and then as time progresses, this one changes. So this one actually moves, goes to another position. So the probabilities of various observations also change. So as it moves, at some point of time, the probability of observing this eigenvalue will become 0. With we'll be able to observe this eigenvalue with 100% probability, and so on and so forth. As psi changes, the probabilities also change. Now, you might imagine another way of looking at the thing where you assume that the psi does not change. Instead, the basis vectors change. So it becomes like this. And as a result, the projections also change. And what we wanted to observe remain the same, because all we want to know are the what we can observe. These are the eigenvalues, and with what probability we can observe these. These are the projections. So there are two possible alternative ways of picturing it. One is where the basis or the operators do not change, but the psi changes, and as a result the projections change. Or the psi remains stays put, but the operators change, and as a result their basis vectors also change, and as a result the what we obtain as the projection also remains the same. These are the two possible ways of seeing it. This way of seeing it is called the Schrodinger picture, which we learned so far. This is something that Schrodinger showed us. We call it picture. It is a way of picturing what is happening in the quantum domain. And we picture it as stays put, wave function evolves. Well, Heisenberg proposed another picture in which the opposite happens. The wave function stays put and the operators evolve. Operators means these are matrices. The matrix elements change with time. Okay, so let us now work that out, how that representation comes into or give written in the middle. I'll just delete it and write at the top. In these two pictures, when we represent, I will put a subscript s to mean the psi. S will mean this is the Schrodinger picture. Okay. And we'll put Heisenberg as the subscript. So this is the Heisenberg. So what we just learned, which I wrote and then deleted, was that the Schrodinger state function evolves as I h cross d dt psi s. I'll just write function of time. Is dependent on h, operating on psi Schrodinger. And this we said that this leads to the result that psi Schrodinger as a function of time evolves as e to the power minus I h operator t by h cross psi Schrodinger at 0. Okay. So this was the Schrodinger picture of the evolution of this state. Now Heisenberg said that I want my state to stay put. And so the Heisenberg wave function that happens if the Heisenberg wave function is defined as just the opposite of this, e to the power plus I h operator t by h cross, then it is psi Schrodinger. So if it is defined this way, then obviously the psi Heisenberg at any particular time, so it will be e to the power, sorry, this is at any particular time, this will be this first, e to the power I h operator t by h cross times is this. So e to the power minus I h by h cross psi s, and this to cancel off. So only this remains. And also you can see that if you define it this way, that at t is equal to 0, the two pictures give the same result. So psi h at 0 is the same, sorry, is the same as psi Schrodinger at 0. At the initial condition, these two pictures are the same. But after that, what happens is that the Heisenberg wave function does not change at all, because this cancel off, and ultimately it remains put at this is psi Heisenberg at 0, same thing. So it remains whatever it was at 0th time. But what happens is that the any operator will change. So the way it's defined is that any operator A in the Heisenberg operator in the Heisenberg representation will become now a function of time, and it actually follows the coordinate transformation that we have learned about, the basis transformation that we learned about earlier. So all we'll have to do is to put the this one e to the power I h operator t by h cross. This comes first, and then a Schrodinger, any operator in the Schrodinger domain, which is not a function of time, times e to the power minus I h t by h cross. Now, if you define any operator in the Heisenberg domain this way, you know what this is, but you now define this in this way, then it becomes a function of time. But the advantage is that if you now work with this as the operator, then you get certain advantage of it. For example, okay, I'll show the advantages a little later. First, let us see if the operator were the Hamiltonian operator. Then what? The Hamiltonian operator in the Heisenberg domain, then that will be e to the power I, the Hamiltonian operator, t by h cross, the Hamiltonian operator in the Schrodinger domain, e to the power minus I h operator t by h cross. Now, the Hamiltonian operator commutes with any function of the Hamiltonian operator. So these two can be exchanged, and naturally this and that cancels off. It becomes equal to the Hamiltonian operator in Schrodinger domain, which means the Hamiltonian operator does not really change when you go from one picture to another. The other operators change, but the Hamiltonian operator will not. Others operator would change if that does not commute to the Hamiltonian. So now let us start with, where is it here? Let us give a number, and let us see how it changes with time. So I want to figure out d dt of a Hamiltonian. This is what we are trying to figure out. If you want to figure that out, then you get you have to differentiate this with respect to time. It has three terms, so there will be three added quantities in the derivative. First, let us take a derivative of this and keep this one as it is. So it is I h operator by h cross. Then the rest remain the same. I h operator t by h cross a s e to the power minus I h operator t by h cross. Okay, the first term differentiation done. Now let us differentiate the last term. So it is minus, that will come out, minus I H operator by H cross. The rest remains the same. E to the power I H operator T by H cross AS e to the power minus I H operator T by H cross. So the first two differentiations done. The third one will be the derivative of this one. So it is right here, plus e to the power I H operator T by H cross. First term done. Second term is then derivative of AS with respect to time. It can be a function of x also, therefore we have to take a partial derivative. And then you have e to the power minus I H operator T by H cross. Okay. So now we have a situation where we can now simplify these, and the simplification happens because the Hamiltonian operator commutes with this, and therefore the Hamiltonian operator can be brought here. The Hamiltonian operator commutes with this, the Hamiltonian operator can be brought here. So this essentially becomes I by H cross, and then when it is brought the other side, then these terms cancel off. So it becomes effectively so notice your this term, this whole term was actually this. This whole term was actually this. So this term is H, AH. This term is H. Then you can bring it forward. So it becomes effectively A, H, and the Hamiltonian operators commutator. These two terms, plus if this does not commute with this, then this can be brought out and these two cancel off. So effectively what remains is this is how should I put it? This is effectively the derivative of the A Hamiltonian with respect to time, because this times AS times this was the age, therefore it is effectively, when you take a derivative with respect to time, it's only this much. So this is very similar to what we obtained earlier as the generalized Ehrenfest theorem, only with the addition of this term here, because at that time we assumed that the operator does not change with time, but here it might change with time. Therefore, if there is explicit dependence of the operator on the time, then this will be representing the explicit dependence. And this if explicit dependence is not there, then obviously this term will go to zero and you only land up with only this much. Okay. So you see, how does the operator change with time? It changes with time as a differential equation given by, sorry, a simple looking equation. And what Heisenberg said is that there are two possible ways of looking at the evolution dynamics. In my picture, I will picture the any operator evolving by means of this kind of a differential equation. So it's a matrix, and that matrix elements will change with time. But then at any point of time, if I want to find out what is happening, all I need to do is to find out the operator at that time and operate it on the state vector. State vector doesn't vary with time. because we have already ensured the state vector will not vary with time. Okay? State vector at any time is the same as the state vector in the Heisenberg picture. So, okay, at this stage, let me stop for some time because I'll have to illustrate this next using a system that you already know, for example, the harmonic oscillator, how actually it works. Effectively, the Schrodinger picture and the Heisenberg picture are completely equivalent because it will ultimately give rise to exactly the same results, the results that you want to learn, but these are two different ways of doing it. It is true that in the first year or the last year and the rest of this semester, we have only followed the Schrodinger picture. But there are situations in which the Heisenberg picture gives a lot of advantage, especially you will see in the next year, where you will need to use the Heisenberg picture, and therefore it's necessary for you to know what it is. So at this stage, let me just stop for a while and invite questions. Do you have any questions on what we did, this particular picture?
So,
Yeah.
sir, why in the derivation shouldn't there be a del AS if AS is dependent on position? So shouldn't there be a del AS del x into x dot term over there because you are doing a total derivative of A?
But the thing is, AH, like the position or the momentum is just a representation, right? I mean,
Right.
like AS, should it really explicitly depend on position or momentum? I don't think so. Like in that sense.
Anubhav just said makes sense because this does not have a explicit dependence on the position. These are variables that appear in the expression. That's all. It will contain variables, but there is no explicit dependence. Explicit dependence and sort of implicit dependence are two different things, right?
Yes, sir. But,
Yeah. So in that sense, the AS does not have the explicit dependence on other things. These are the variables like x and p. These things are there, but these are not explicit dependence. If x is this, then the h will be that. That kind of dependence is not there. In that sense,
Yeah, I
yes, sir.
mean, if you think of it like a matrix, like
yeah.
if you just change, if you go from one point to other, the matrix operator won't change, right? So in that sense.
Somebody else was also asking question. Who?
Sir, can you hear me?
Yeah,
Okay. In the expression of dAH
yeah,
sir, in the second term you have written it like IH bar by H cross. In the second
yeah,
term,
yes.
shouldn't be it on the right side because we don't know if A is commutes with H yet.
Very good point. Very good point. Yes, very good point. This actually should come here. You're right. Because H, we do not know if it commutes with these guys. You're right.
Sir, another thing that here you have written del AH del T, but I think it should be like the Heisenberg picture of the whole thing, like a del A del T in the whole thing in Heisenberg picture, and not like del AH del T, probably, because like we are taking e to the power.
In which picture?
So in the last line,
Last line. Yes.
yeah. Where you have shown the explicit dependence thing with the arrow.
Yeah.
So the thing is that we are taking e to the power I h roof t by h cross del as del t, and then the other u operator. So it should be like del a del t, like the Heisenberg picture of del a del t, right? Like not the del a h del t, probably.
Heisenberg picture of deleted. Not a
I
bad,
mean that del a
not a
del
bad
t
point at all.
whole
Wait.
h.
No, no,
Yeah,
no, no,
yeah.
not a bad point at all. So you mean to say it is something like this? It is the Heisenberg picture. You want something like this?
Yes, yes, yes.
Huh?
Yeah, yeah.
But A is either in the Schrodinger picture or in the Heisenberg picture. So A just standing alone will not make much sense. So you mean to say that see A standing alone will make much sense. Either it is in the Schrodinger picture or in the Heisenberg picture. It was in the Schrodinger picture, which its derivative in the Schrodinger picture converted to the Heisenberg picture. That's what it actually is. Yes, you're right. So effectively, it is that is what is sort of customary to write del A is del T. But yes, you are right. You take a derivative of the Schrodinger picture and convert that into Heisenberg picture, and that is what we are talking about, right?
Yes, sir.
Yes, uh, that is right. That is right. So you have the derivative taken of the Schrodinger picture, Schrodinger operator, and then you convert it into the Heisenberg picture. Yes, that's right. That is right. That's another way of looking at it.
Now I show the result obtained by one of the students in the first assignment, and for this student the x-axis is the eigenvalue number, that means the first eigenvalue, second eigenvalue, and the value of the eigenvalue is plotted in the y-axis. So at the first one it will be half, second one will be 3/2, and so on and so forth. So that would be the theoretically predicted one for the harmonic oscillator, as you know, and the numerically obtained one, that means simply extracting the eigenvalue of the matrix, Hamiltonian matrix that you obtain, that is also plotted here. The points actually are so close together that you cannot really make out the difference. Only you can see that towards the end it is a bit longish here in this direction, which means that slight difference is there, but over the first 10 eigenvalues you cannot really make out the difference. So this method of calculating the eigenvalues is reasonably accurate. Let's go to the eigenvectors, and this is the ground state eigenvector. Eigenvector in the matrix, as you know, yields the eigenfunction. So at each of these points on the x-axis, this is how the x-axis is divided into various segments, and at each point the value that you get, if you plot that, you get the eigenfunction, and that way this eigenfunction has been plotted, the ground state eigenfunction, or mod psi naught square, and you can see that it's very close to the theoretically predicted value. Theoretically predicted values are given in the dots, and the numerical obtained one is the blue line. This is the ground state. This is the sixth excited state, mod psi square of the sixth excited state, and the third excited state of the system. And as you can see that the computation by the matrix method is quite easy and reasonably accurate. Actually, the errors start showing up from the extremities, because in the extremity of the matrix, the 1 element and the n element, these are a bit inaccurate, because there you are embodying the second derivative in the form of a matrix element, and there you need to put also the left, the element that is there to the left hand side of that, and for the last one to the right hand side of that, which you could not, because there is a extremity of the x-axis minus 30 to 30. So the errors start propagating from there. But if you divide the x-axis into a reasonably large number of segments, then it really gives a reasonably accurate thing, so that here in the only if you go to far larger, far higher eigenvalues, then only these two will start to deviate from each other. Otherwise you get reasonably accurate results by the method that I showed, the matrix method.